Carbonation, the magic behind your favorite fizzy drinks, boils down to a simple concept: dissolving carbon dioxide gas, or CO2, into water, H2O. Sounds easy, right? Well, not quite. Under normal circumstances, CO2 isn't too keen on mixing with water. It prefers to exist as a gas. That's where the science comes in. To create that refreshing effervescence, beverage manufacturers employ a clever trick. They pump CO2 into the liquid under high pressure, forcing the gas to dissolve. Think of it like trying to squeeze a bunch of marbles into a jar. The more pressure you apply, the more marbles you can fit. This process transforms ordinary water into a supersaturated solution, meaning it's holding more CO2 than it normally could at standard atmospheric pressure. But this state is temporary, as you're about to find out. Pressure play, the key to carbonation. The secret to keeping all that CO2 dissolved lies in maintaining a delicate balance of pressure. Inside a sealed can or bottle, it's a high-pressure environment. This pressure forces the CO2 molecules to stay crammed within the liquid. It's like holding a beach ball underwater. The water pressure keeps it submerged. However, the moment you crack open a can or twist off a bottle cap, the game changes. The internal pressure plummets, and the CO2 molecules are suddenly free to escape their liquid prison. They rise to the surface as tiny bubbles, creating that characteristic fizz we all know and love. The higher the pressure during production, the more CO2 can be dissolved, resulting in a fizzier drink. That's why some sodas seem to pack a more intense bubbly punch than others. It's all about the pressure. Inside a sealed bottle of Bubbly, a fascinating dance of equilibrium takes place. The CO2 exists in two states, dissolved in the liquid and as a gas trapped in the space above the liquid. These two states are constantly interacting, striving for balance. Imagine a seesaw with dissolved CO2 on one side and gaseous CO2 on the other. When the seesaw is balanced, you have equilibrium. The pressure exerted by the gaseous CO2 prevents the dissolved CO2 from escaping. It's like the two sides of the seesaw holding each other in check. This balance is crucial for maintaining the fizz. If the pressure inside the bottle drops, say, due to a tiny leak, the equilibrium is disrupted. The dissolved CO2 seizes the opportunity to escape and your drink will go flat. The satisfying hiss you hear when opening a can of soda is more than just a sound. It's the sound of pressure escaping and equilibrium being shattered. As the internal pressure rapidly drops to match the atmospheric pressure outside, the dissolved carbon dioxide breaks free. Remember those carbon dioxide molecules crammed into the liquid? They're now free to party. They form tiny bubbles that rise to the surface, eager to escape their liquid confines. The smoother the surface of the container, the easier it is for bubbles to form and rise. This is why sodas tend to fizz more aggressively if you pour them over ice. The rough surface of the ice cubes provides numerous nucleation sites for bubbles to form. It's like giving those carbon dioxide molecules a playground to release their pent-up energy. Carbonation does more than just tickle your taste buds with bubbles. It also adds a unique tang to your drink. This is the work of carbonic acid, a weak acid formed when carbon dioxide dissolves in water. The chemical reaction is simple. Carbon dioxide plus water reacts to form carbonic acid. This weak acid is responsible for the slightly tart, citrusy flavor we associate with carbonated drinks. Interestingly, carbonic acid also acts as a mild, antibacterial agent. It creates an acidic environment that's not particularly hospitable to bacteria, helping to prolong the shelf life of your favorite sodas and sparkling waters. So, the next time you enjoy a fizzy drink, thank carbonic acid for that refreshing tang and its role in keeping things fresh. Ever notice how diet sodas seem to hold their fizz longer than their sugary counterparts? The secret lies in surface tension, the force that makes the surface of a liquid behave like a stretched elastic sheet. Water, the main ingredient in sodas, has a relatively high surface tension. However, artificial sweeteners, commonly found in diet drinks, can reduce this surface tension. This might sound like a bad thing for bubbles, but it's quite the opposite. Lower surface tension means bubbles can form more easily and last longer. Think of it like blowing bubbles with soapy water. The soap reduces the water's surface tension, allowing you to create bigger, more durable bubbles. The same principle applies to diet sodas. So, while the difference in fizz longevity might seem subtle, it's all thanks to the fascinating interplay between artificial sweeteners and surface tension. Temperature plays a crucial role in the carbonation game. As you might have guessed, carbon dioxide is more soluble in cold water than in warm water. This means that a cold soda can hold more dissolved carbon dioxide, resulting in a fizzier experience. Think about what happens when you leave a can of soda out in the sun. The heat causes the carbon dioxide molecules to become more energetic and eager to escape the liquid. This leads to a less bubbly drink, as much of the carbon dioxide has already fizzled away. On the other end of the spectrum, freezing a carbonated drink is a recipe for disaster. As water freezes, it expands, forcing the dissolved carbon dioxide out of solution. This can create immense pressure inside the container, potentially causing it to explode. So, the next time you reach for a refreshing bubbly beverage, remember the delicate dance of temperature and carbonation. Keep it cold for maximum fizz and avoid the freezer at all costs.